Welcome to this problem-solving session. In today's video, we'll be tackling LeetCode problem number 1416, Restore the Array. This problem challenges us to find the number of ways to split a string into valid substrings based on certain rules. Let's dive in and explore the approaches to solve this problem step by step. In this problem, you are given a string s, which contains only digits, and an integer k. The goal is to determine the number of valid arrays you can form by splitting the string s into non-empty substrings. These substrings must meet a few criteria. First, when concatenated, they should reconstruct the original string s. Second, each substring must represent a number that falls within the range from 1 to k, inclusive. Third, no substring can have leading zeros. This means substrings like 01 foot or 0001 are not allowed. Since the number of valid arrays can be very large, the final result must be returned modulo 10 to the power of 9 plus 7. The problem also comes with constraints. The length of s can go up to 100,000 characters, and k can be as large as 1 billion. This makes finding an efficient solution critical. To help clarify the problem, let's look at some examples. In the first example, the string s is 1000 and k is 10,000. The output here is 1. This is because there is only one valid way to split the string, 1000. The number 1000 is within the range, 1, 10,000, and there are no leading zeros in this substring. So, the result is straightforward, there is exactly one valid array. Now, consider the second example where the string is still 1000, but this time k is only 10. The output here is 0, meaning no valid arrays can be formed. The reason is that the number 1000 exceeds the maximum value of 10 allowed by k. Additionally, splitting the string into smaller substrings, like 1, 0, 0, 0, is invalid because the substring 0, 0, 0 has leading zeros. Therefore, no valid way to split the string satisfies the conditions, and the result is 0. In a more complex example, let's say s is 1317 and k is 2000. The output in this case is 8, as there are 8 valid arrays. These arrays are 1, 3, 1, 7, 1, 3, 17, 1, 31, 7, 1, 317, 13, 1, 7, 13, 17, 131, 7, and 1317. All these arrays satisfy the conditions. Each substring represents a number within the range, 1, 2000, and none of the substrings have leading zeros. This demonstrates how different combinations of splits can form multiple valid arrays. To handle edge cases, consider scenarios where k is very small or very large. For example, if k is extremely small, such as 1, only the substring 1 is valid if it appears in S. On the other hand, if k is very large, such as 10 to the power of 9, then all valid numbers in S that fall within the range, 1, k, are acceptable, provided there are no leading zeros. Additionally, when the string s is very long, efficient approaches like dynamic programming are essential to process the constraints without exceeding time limits. These considerations highlight the importance of designing an optimized solution for this problem. To solve the problem Restore the Array, our goal is to determine how many ways we can split the string s into non-empty substrings, ensuring that each substring represents an integer within the range, 1, k. The result must be returned modulo 10 to the power of 9 plus 7. Since the problem involves overlapping subproblems and requires calculating optimal subsolutions, it is well suited for dynamic programming. Initially, we considered a brute force approach. The intuition behind this method is to generate all possible ways to split the string into valid substrings, then verify if each split meets the criteria. Specifically, the substrings must not start with 0 and their values must be less than or equal to k. While this approach is conceptually straightforward, it is computationally expensive because it explores all possible splits, making it impractical for large inputs. The brute force approach has exponential time complexity since it tries every possible split of the string, and its space complexity is also high due to the recursive stack usage. This makes it infeasible for larger inputs where the number of splits grows rapidly. To address these limitations, we turn to an optimized dynamic programming approach. The key idea here is to avoid exploring all splits explicitly by using a bottom-up strategy. We define dp, I, as the number of ways to split the substring s, 0i, into valid parts. Starting from the first character, we work backward to check all possible substrings ending at the current index and accumulate the number of ways from dp, j, for valid splits. For a substring s, j, I, to be valid, it must not start with 0 and its value must be less than or equal to k. The base case is simple, dp, 0, equals 1, meaning there is one way to split an empty string. To keep our computations efficient, we use modular arithmetic to prevent overflow and ensure the result remains within the required limits. To further optimize the dynamic programming solution, we can apply a sliding window technique. Instead of recalculating the validity of substrings for every transition, this approach maintains a running sum of valid splits using a window_sum. The idea is to dynamically update the contribution of dp, j, values to dp, I, as valid substrings are added to or removed from the window. This reduces redundant computations and makes the process more efficient. Specifically, dp, I, is simply assigned the value of window_sum, which is updated as we slide through the string. This optimization brings the time complexity down to O, n, in most cases, as each character is processed at most twice, while the space complexity remains O, n, for the dp array. Although this method is highly efficient, it introduces additional complexity in implementation, which may not always be necessary depending on the constraints of the input. Ultimately, we chose the optimized dynamic programming approach for its balance between clarity, efficiency, and ease of implementation. While the sliding window technique is faster, its added complexity is only justified for extremely large constraints. The brute force method, on the other hand, was rejected due to its exponential time complexity, which makes it impractical for solving this problem. The optimized dp solution iteratively computes the dp array by checking each possible substring s, j, I, for validity, ensuring correctness while maintaining efficiency. Modular arithmetic is used throughout to keep the results within the required limits. In terms of trade-offs, the brute force approach is simple but slow, the sliding window method is fast but complex, and the optimized dp approach strikes the right balance. This makes it the preferred choice, as it effectively meets the problem's requirements without unnecessary complexity. In this problem, we are tasked with restoring an array by determining how many ways we can split a string s into non-empty substrings such that each substring represents an integer within the range from 1 to k. The result must be returned modulo 10 to the power of 9 plus 7 to handle large numbers. To approach this, we need to understand a few key aspects. First, the substrings must represent valid integers, meaning they cannot have leading zeros unless the entire substring is just 0, which is invalid as the range starts from 1. Next, we use a dynamic programming approach to efficiently calculate the number of ways to split the string. Here, we define dp, I, as the number of valid ways to split the prefix of length I from the string s. Finally, since the result can grow very large, we apply modulo arithmetic at every step to ensure that our calculations remain manageable and do not overflow. These insights lay the foundation for our solution. Now, let's break down the algorithm step by step. First, we initialize our variables. We define n as the length of the string s and create a dynamic programming array dp of size n plus 1, initialized to 0. We set dp 0 equals 1 because there is exactly one way to split an empty prefix, which serves as our base case. We also define mod equals 10 to the power of 9 plus 7 for performing modulo arithmetic. Next, we iterate through the string. For each index I from 1 to n, we calculate dp, I, by examining all possible substrings that end at position I1. Specifically, for each potential starting point j, we extract the substring s, j, I, and check if it is valid. A valid substring must not have leading zeros and its integer value must be within the range from 1 to k. If the substring meets these criteria, we add dp, j, to dp, I, as splitting at j leads to a valid partition. To optimize the process, we terminate the inner loop early if the integer representation of the substring exceeds k. Finally, after processing all indices, the value dp, n, contains the total number of valid ways to split the string, which is our result. To implement this solution, we rely on a dynamic programming array dp. This array has a size of n plus 1 and stores the number of ways to split the prefix s, 0, I, into valid substrings. The dp approach is crucial because it allows us to break down the problem into overlapping subproblems, enabling efficient computation. Let's analyze the complexity of the algorithm. For time complexity, the outer loop runs n times, and for each iteration, we may examine up to m previous indices, where m is the maximum length of a valid substring, approximately log 10, k. This results in a time complexity of O, n asterisk m. The space complexity is O, n, because we only need the DP array to store intermediate results. This combination of efficient space and time usage makes the solution well suited for the problem constraints. To better understand the algorithm, let's walk through an example. Suppose the input string s is 1317 and k is 2000. We start by initializing dp, 0, equals 1 as the base case. For I equals 1, the substring s, 0:1, is 1, which is valid. We update dp, 1, equals dp, 0, equals 1. For I equals 2, the substrings s, 1:2, 3, and s, 0:2, 13, are valid, so we update dp, 2, equals dp, 1, plus dp, 0, equals 2. For I equals 3, the substrings s, 2:3, 1, s, 1:3, 31, and s, 0:3, 131, are valid, leading to dp, 3, equals 4. For I equals 4, the valid substrings are s, 3:4, 7, s, 2:4, 17, and s, 1:4, 317, so dp, 4, equals 7. The final result is dp, 4, equals 7. Considering edge cases, inputs like 1 foot are invalid due to leading zeros, large k values must be handled efficiently, and small inputs like 1 should produce correct results. Optimizations include exiting the inner loop early when a substring exceeds k and ensuring string-to-integer conversions are efficient to minimize unnecessary computation. This solution implements a dynamic programming approach to solve the problem of restoring the array. The function number of arrays takes as input the string s and the integer k. Key steps. 1. Initialization. The constant mod is set to 10 to the power of 9 plus 7 to handle large numbers. The length of the string s is stored in n. A list dp of size n plus 1 is created, where dp, I, represents the number of ways to split the substring s, I into valid integers. It is initialized to 0. The base case is dp, n, equals 1, indicating that there is exactly one way to split an empty suffix. 2. Iterative dp calculation. The loop iterates backwards through the string s, from n1 to 0. This ensures that smaller subproblems are solved first, which are then used to solve larger subproblems. If s, I, equals 0, no valid number can start with 0, so dp, I, is set to 0. 3. Building numbers and checking validity. A nested loop iterates through the substring starting from I and constructs the number digit by digit. If number k, the loop breaks since no further valid substrings can be formed. Otherwise, the value of dp, I, is updated by adding dp, j plus 1, the number of ways to split the remainder of the string, modulo mod. 4. Return the result. After processing all indices, dp, 0, contains the number of ways to split the entire string s into valid integers, which is returned as the result. This approach ensures that the solution is computed efficiently in O, n squared, time in the worst case, where n is the length of the string s. The use of modular arithmetic ensures that the result does not overflow for large values of s and k. Here, we begin with the Java implementation of the restore the array problem. First, we import the necessary packages and define our solution class. The core logic is in the method number of arrays, which takes a string s and an integer k as input. The variable mod is defined to handle large results by taking modulo 10 to the power of 9 plus 7, ensuring we avoid overflow. Next, we determine the length of the string s and initialize a dynamic programming array, dp, of size n plus 1. This dp array will store the number of ways to split the substring starting from each index. The base case is set such that dp, n, equals 1, representing one way to split an empty suffix. Now, we use a reverse iteration starting from the second to last character in the string. At each position I, we first check if the current character is 0. Since a valid number cannot start with 0, we set dp, I, to 0 in this case. Otherwise, we initialize a variable number to 0 and use a nested loop to build numbers by appending characters one by one from index I. As soon as the constructed number exceeds k, we break the inner loop. If the number is valid, we update dp I by adding the number of ways to split the substring starting from index j plus 1, taking modulo mod to ensure results fit within the allowed range. The implementation concludes with the return statement, where we return dp 0. This represents the total number of ways to split the entire string s into valid integers that satisfy the condition of being less than or equal to k. By utilizing dynamic programming, we efficiently compute the result while considering all valid splits and avoiding redundant computations. The modular arithmetic ensures our solution is robust against large intermediate results. This concludes the Java implementation for the problem. In this example, we are working with the string 1317 and the maximum value k equals 200. The length of the string, n, is 4. We initialize our dp array with a base case where dp, n, is set to 1, representing the one way to split an empty suffix. This gives us dp equals 0, 0, 0, 0, 1. Starting with I equals 3, we observe that the character 7 does not have a leading 0, so we compute the number represented by this character. Since 7 is less than or equal to k, it is valid. We then update dp 3 by adding dp 4, resulting in dp 3 equals 1. At this point, the dp array becomes 0, 0, 0, 1, 1. Next, we analyze I equals 2, where the character is 1. Again, there is no leading 0, so we compute numbers starting from this index. The first number, 1, is valid because it is less than or equal to k, so we add dp 3 to dp 2, updating dp 2 to 1. Then, we extend the number to 17, which is also valid. We add dp 4 to dp 2, updating dp 2 to 2. Moving on to I equals 1, the character is 3, which again has no leading 0. We compute the number 3, which is valid, and update dp 1 by adding dp 2, resulting in dp 1 equals 2. Extending to 31 foot, we find it is still valid, so we add dp 3 to dp 1, updating dp 1 to 3. However, when we extend further to 317, it exceeds k, so we stop. The dp array now looks like 0, 3, 2, 1, 1. For I equals 0, the character is 1. We first compute the number 1, which is valid, and add dp 1 to dp 0, updating dp 0 to 3. Extending to 13, we find it is valid, so we add dp 2 to dp 0, updating dp 0 to 5. Then, we compute 131, which is also valid, and add dp 3 to dp 0, updating dp 0 to 6. Finally, we attempt 1317, but it exceeds k, so we stop. The final dp array is 6, 3, 2, 1, 1, and dp 0 equals 6, indicating there are 6 ways to split 1317 into valid integers. In the second example, we work with the string 2020 and k equals 10. The initial dp array is set to 0, 0, 0, 0, 1. For I equals 3, the character is 0, and since a number cannot start with 0, dp 3 remains 0. Moving to I equals 2, the character is 2, which is valid. We compute the number 2, find it is less than or equal to k, and update dp 2 by adding dp 3. However, since dp 3 is 0, dp 2 remains 0. At this stage, the dp array is still 0, 0, 0, 0, 1. For I equals 1, the character is 0. Again, since numbers cannot start with 0, dp 1 remains 0. Finally, at I equals 0, the character is 2. We first compute the number 2, which is valid, and add dp 1 to dp 0. However, since dp 1 is 0, dp 0 remains 0. When extending to 20, we find it exceeds k, so we stop. The final dp array is 0, 0, 0, 0, 1, and dp 0 equals 0, meaning there are no valid ways to split 2020 into integers that satisfy the conditions. In this third example, we analyze the string 123 with k equals 50. The initial dp array is 0, 0, 0, 1. For I equals 2, the character is 3. Since there is no leading 0, we compute the number 3, which is valid as it is less than or equal to k. We update dp2 by adding dp3, resulting in dp2 equals 1. The dp array becomes 0, 0, 1, 1. For I equals 1, the character is 2. We first compute the number 2, which is valid, and add dp2 to dp1, updating dp1 to 1. Extending to 23 foot, we find it is also valid, so we add dp3 to dp1, updating dp1 to 2. At I equals 0, the character is 1. We compute the number 1, add dp1 to dp0, and update dp0 to 2. Extending to 12, we find it is valid, so we add dp2 to dp0, updating dp0 to 3. However, when we compute 123, it exceeds k, so we stop. The final dp array is 3, 2, 1, 1, and dp0 equals 3, indicating there are 3 ways to split 123 into valid integers. The time complexity of our algorithm is determined by the nested loop structure. The outer loop iterates through the string from the last index to the first, which gives us a total of n iterations. For each iteration of the outer loop, the inner loop tries to expand the substring starting at the current index I and ending at index j to form a valid number. In the worst case, the inner loop can iterate up to n 1 times for each value of I. When we sum up all these iterations across the outer loop, we get a series, n plus n1 plus n2 plus 1, which simplifies to n asterisk n plus 1 slash 2. This is a triangular number and grows asymptotically as O, n squared. There is also a breaking condition in the inner loop that stops early if the number exceeds k, but this does not change the worst case analysis since, when k is very large, all substrings can still be valid. Therefore, the overall time complexity remains O, n squared, in the worst case. Within the inner loop, the operations we perform, such as updating the variable number in any modular arithmetic, are constant time operations, meaning they each take O, 1, time. These operations do not influence the asymptotic time complexity, which is dominated by the nested loop structure as explained earlier. Shifting focus to space complexity, the primary contribution comes from the dynamic programming array, or DP, which is of size n plus 1. This array is used to store the number of ways to split the substring starting at each index, and thus requires O, n, space. Apart from the DP array, we have a few auxiliary variables, such as number and loop counters, which take up only constant space, or O1. When we combine these, the overall space complexity of the algorithm is O, n, dominated by the storage for the DP array. Now, let's analyze the best, average, and worst case scenarios. In the best case, if the value of k is very small, the inner loop will terminate early for most indices because substrings will quickly exceed k. While this reduces the number of iterations within the inner loop, the outer loop still runs n times, resulting in an overall time complexity of O, n. In the average case, the inner loop typically runs for a moderate number of iterations, depending on k and the structure of the string. However, summing these iterations across all indices still results in O, n squared, as the nested loop dominates. In the worst case, when k is very large or when the string contains only valid substrings, the inner loop runs the maximum number of iterations for every index. This gives us the maximum number of operations, and the time complexity remains O, n squared. When comparing our optimized dynamic programming approach to a brute force solution, the efficiency becomes clear. A brute force approach would involve generating all possible splits of the string and checking if each split is valid. This results in 2n1 possible splits for a string of length n, leading to an exponential time complexity of O, 2 to the power of n. Additionally, the space complexity would also be higher due to the need to store intermediate splits. In contrast, our dynamic programming solution avoids redundant calculations by storing results for overlapping subproblems. This reduces the time complexity to O, n squared, and the space complexity to O, n. Mathematically, the inner loop's total iterations can be represented as a triangular number, which simplifies to O, n squared. Therefore, by leveraging the DP array, we achieve a significant improvement in both time and space efficiency compared to the brute force method. When solving this problem, there are several common mistakes to watch out for. First, handling leading zeros improperly can be a pitfall. Remember, substrings like O1 foot are invalid integers, so always validate that no substring starts with a 0. Next, it's critical to ensure that each substring falls within the allowed range of 1 to k. If you overlook this, the solution can produce incorrect results. Another frequent issue is inefficient computation of substrings. Generating all possible substrings repeatedly can be very costly and may lead to exceeding time limits. Instead, leverage dynamic programming to avoid redundant calculations. Additionally, modulo arithmetic is often overlooked. Since the results can grow very large, especially in languages like Java or C++, make sure to apply the modulo operation at every step to prevent integer overflow. Finally, be cautious with the initialization of the dynamic programming array. Forgetting to set the base case, such as dp 0 equals 1, can cause the entire solution to fail. Always ensure that the dp array is initialized properly before proceeding. This problem is an excellent test of your ability to apply dynamic programming effectively, particularly in scenarios constrained by numeric ranges. The core idea is to count the valid ways to split the string while adhering to these constraints. A well-defined DP state and efficient substring validations are key to solving this problem. During interviews, it's important to highlight your thought process in optimizing substring validation because brute force approaches won't scale for large inputs. For instance, converting substrings to integers should be done efficiently. Interviewers may also challenge you by introducing variations, such as restricting substrings to a different range like 10k, or adding new constraints, such as a maximum allowable split length. Demonstrating adaptability to these changes is a great way to stand out. There are several related problems that can help deepen your understanding of this concept. For example, LeetCode 91, Decode Ways, involves a similar dynamic programming approach to count valid decodings of a string based on specific constraints. Another is LeetCode 139, Word Break, which also involves using DP to split a string into valid words from a dictionary. While not directly related in topic, LeetCode 42, Trapping Rainwater, is a great example of efficiently handling constraints and ranges, a skill that's transferable to this problem. Lastly, LeetCode 131, Palindrome Partitioning, focuses on splitting strings into parts that meet a specific condition, in this case, palindromes. These problems collectively build the intuition and techniques you can apply to restore the array. There are multiple approaches to solving this problem, each with its own trade-offs. A brute force method involves trying all possible splits and validating each substring. While simple to implement, this approach has exponential time complexity, 2 to the power of n, and is impractical for large inputs. Recursive backtracking is another option, where you recursively split the string and validate substrings while memoizing results to avoid redundant computations. This method is easier to understand but slower than iterative dynamic programming due to its overhead. The most optimal approach is iterative dynamic programming, where you use a DP array to track the number of valid splits up to each character. By iterating through valid substrings and updating DP states, you achieve a time complexity of n*m, where m is the maximum length of valid substrings. For very large ranges of k, a sliding window optimization can be used to reduce the overhead of substring validation further. While this is highly efficient under specific constraints, it increases implementation complexity, so it's important to balance efficiency and clarity based on the problem requirements. Great work! To wrap up, we reviewed the dynamic programming approach and learned how to optimize for this problem. Remember to practice similar problems to strengthen your understanding. Don't forget to like, subscribe, and stay tuned for more problem-solving sessions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!